All right, the focus of this set of notes is continuity. This is lesson 2.5a. All right, we say that a function f is continuous at a if the following conditions are met. 1, f of a is defined. That is, a is in the domain of f. 2, the limit of f of x as x approaches a exists. And 3, that the limit of f of x as x approaches a is equal to where it's defined. That is, we approach from left and right, and where we approach is where it's defined. The graph of a function f is shown in the figure below. Use the graph to determine whether the function is continuous at 1, at 3, and at 5.
Play the daily question.
All right, so let's take a look at -1. Or sorry, at +1. At 1, the function is discontinuous because, well, our first condition is not met. F of a is not defined. Okay, so we would state that f is not continuous at x equals 1 because the function is not defined at 1. That is, f of 1 is undefined. Now, at 3. At 3, it is defined. The problem is that the limit does not exist. When we approach from the left, 3, we get -1. When we approach 3 from the right, we get 2. So condition 2 is not met, thus it is not continuous at 3. Now at 5. At 5, the limit exists. From left and right, we approach 1. The function is in fact defined. We see that at f of 5, we get an output of 3. The problem is the limit is 1, but the function is defined at 3, thus discontinuous at 5. Determine whether each function is continuous at the given value. So let's check. So condition 1, is f of 2 defined? So we have 2 squared minus 2 over 2 minus 2, which is 0 over 0. That is undefined. Therefore, not continuous. At x equals 2. Okay, let's check B. Okay, is g of 0 defined? It is. It's defined as 1. All right, now let's check the limit. So the limit as x approaches 0 of g of x is 1 over x squared. We have to approach 0 from the left. And let's approach 0 from the right. And actually, that's actually not necessary. Let's just approach 0. Now, here's the problem. Actually, hold on. Yes, 0 from the left and 0 from the right. If I approach 0 from the left, I'm plugging in a really small negative, like a negative 0.0001, and if I square it, it becomes positive. So this is 1 over a really small positive number, and 1 divided by a really small positive is a really big positive. And the same thing happens here. Therefore, the limit does exist, and the limit as x approaches 0 of g of x is in fact infinity. Now, what's our third condition? Our third condition states that the limit must be the same as where the value of the function is defined. Note, g of 0 is 1, but that the limit is infinity. Therefore, we say not continuous. And x equals 0. Determine whether each function is continuous at the given value. So the same idea applies for C and D as what we did before. Test the 3 conditions. Discontinuity can be defined as removable if I could simply fill in the hole by redefining x at that hole. A discontinuity is considered non-removable if there's no value that would fill in the hole. So for example, when you have an asymptote, a single point cannot fill in that gap. And then we have what are called jump discontinuities, and those occur when the graph of the function jumps from one value to another without taking on any values in between. A function is allowed to be continuous from the right if the limit from the right is equal to what the function is defined at. A function can be continuous from the left if the limit from the left is equal to what the function is defined at. And then I'm going to skip the rest of this for right now.